demonstration of liquisolid compact of artemether using Neusilin US32 and Syloid XDP as potential excipients. Coming to the introduction, artemether is a potent, rapidly acting antimalarial drug used in the first-line treatment of multi-drug resistant malaria and is enlisted in the WHO list of essential medicines. It belongs to BCS2 and shows incomplete absorption and low oral bioavailability due to poor dissolution. The clinical efficacy of artemether is greatly affected by its poor aqueous solubility. The other significant factor for its poor bioavailability is that it exhibits two polymorphic forms, alpha and beta. The beta form has higher antimalarial activity due to the presence of endo-peroxide linkage, and this linkage makes the molecule quite unstable due to heat and gets easily decomposed into another two inactive polymorphs. So this requires a special package and precautions in the process of production, storage, and transportation. Considering the above facts, only solubility enhancement of artemether may not be beneficial to improve the bioavailability. It also requires preservation of the bioactive polymorphic form of the molecule. Therefore, a liquisolid compact of artemether might serve as a promising way to preserve its bioactive polymorphic form with enhanced solubility. Liquisolid compact technology involves dispersion of solid drug in a non-volatile solvent where it shows maximum solubility. And then that drug solution is incorporated into the carrier material, and that carrier material is absorbed onto a porous coating material to yield a free-flowing compressible powder mixture. So, mesoporous silicas were selected as the carrier and the coating component as they are reported to be a good excipients for improving solubility due to their enhanced surface area, pore size, and porosity. Hence, the present study aims to assess the role of liquisolid technique in solid state stability and solubility enhancement of artemether using mesoporous silica. The objective of the present research was to screen the efficacy of mesoporous silica as a carrier and coating material for the liquisolid compact at a suitable excipient ratio, enhancement of the dissolution of artemether, and evaluating the polymorphic retention of artemether through surface characteristic study. So in any liquisolid compact, as I discussed earlier, that the non-solvent selection is important. So the non-solvent should be selected depending on the highest solubility of the drug in it. So in our study for artemether, we have selected twin 20, twin 80, PG400, PG600, propylene glycol, and glycerin as different non-solvents, and we have screened the non-solvent by a normal solubility study where we have taken the drug in excess form in a 10 ml non-solvent, and then we have vortexed for 15 minutes, and then we have kept the same mixture for mechanical shaker at room temperature for 48 hours. After that, we have centrifuged, and the supernatant layer was estimated by UV spectrophotometrically with a developed process as mentioned in the IP. Coming to this liquisolid concept, liquisolid compact concept, which involves a mathematical model prescribed by Spireas Bolton. So, as per this model, first, as there are two types of material, one is the carrier material, one is the coating material. So, first we have to find out the liquid retention potential of the carrier and the coating. So this was done by measurement of the angle of slide. Following that, we have to calculate the liquid loading factor, and from there we have to find out how much weight of the liquid we can add into the powder mixture so that the powder retain its flowability and compactability. So using this concept, we have done a screening of excipients, and generally I have taken for this study Neusilin US32, Neusilin US32 and MCC in 9:1 ratio, and Neusilin US32 and MCC in 1:1 ratio as carrier, and Syloid XDP as coating material. So we have found out the angle of slide for all the things, and I found that Neusilin US32 and Neusilin US32 plus MCC at 9:1 ratio gave a good flow property, and later on when we have compressed into a tablet, we could get a good hardness out of it. So we have not taken US32 MCC at 1:1 ratio, but Syloid XDP was used as a carrier throughout the experiments. So now varying the excipients ratio from 5 to 30, we have prepared 6 different formulations, and using Neusilin US32 and 9:1 ratio with MCC as carriers and coating material with Syloid XDP. So this is the formulation chart where we have prepared 6 different formulations, and if we calculate that, we'll find that excipient ratio was varied from 5 to 30, and the first 3 formulation was prepared only with Neusilin US32, whereas the rest 3 formulation was prepared with Neusilin and MCC in 9:1 ratio. So here also the drug artemether was dissolved in 280, and then it was transported, it was absorbed onto the carrier materials, and then that carrier material was coated with the Syloid XDP, the coating material, and then the other excipients like magnesium stearate, cross-carbamylose sodium was added, and finally it was compressed into tablet by direct compression method. So the compact was evaluated for pre-compression characteristics, post-compression characteristics, in vitro dissolution studies, statistical analysis, and we have estimated the specific surface area, and then solid state behavior of the liquid solid compact was established with FTIR, DSC, and PXRD studies, and finally we have concluded with stability study. So the pre and post compression parameters here showed that as the proportion of silica increases, the flowability was increasing, but the compressibility was decreasing. So in case of F5, we have shown that the Cart's index was quite low, and that gave, it was not low, it was optimum, and it gave a good compressibility of the powder. The same effect was observed when the post-compression evaluation was done of, after compression into tablet. So it was seen that friability, hardness, wetting time, disintegration time, they are directly related to the total proportion of the porous material in the compact. So it was seen that if we reduce the proportion of mesoporous silica a bit, it was found to increase the compressibility and offer a good tablet ability. The in vitro dissolution study was carried out, and it was seen all the formulation showed a very good release compared to the pure drug. And then the post-compression data and the pre-compression data was subjected on a ranking scale to select the best formulation out of these 6 formulations. And it was seen that through Pareto analysis, F5 was scoring the highest, and it was taken for further analysis. So F5 was subjected for specific surface area estimation through BET study, and we have compared the BET graph with a placebo formulation of F5. The placebo formulation exhibited type 4 isotherms for typical mesoporous materials and it showed a hysteresis loop in the partial pressure range of 0.6 to 1.05 that indicates poor filling capacity of placebo liquid solid compact containing mesoporous system, whereas the formulation 5 we have done when we have done the BET study, they showed a slight decrease in the surface area and poor volume of the contact, and that indicates drug loading in the mesopores of the carrier and port. But it also indicates in the other way that the effective surface area of the drug was increased significantly. The presence of the unoccupied ports in the liquid solid compact allowed the dissolution media to enter, and probably that must have caused the drug to release through the wicking effect. So when the dissolution efficiency was calculated for the formulation F5 and compared with the pure drug, it was seen that dissolution was improved approximately by 4 times. Hence, the liquid solid compact of artemether with mesoporous silica was found to enhance the dissolution of the drug significantly. Now, coming to establishment of the solid state behavior. So FTIR was carried out for the pure drug and for the formulation F5, and it was shown that in the fingerprint region, the characteristics peaks were intact, and that indicates there were no interactions and perseverance of the beta polymorphic form of artemether. Sorry. In the DSC study, when the formulation was subjected for DSC study, the pure drug showed a sharp endothermic peak at 86.64 degrees centigrade, and the formulation showed a very small peak, indicating a marked reduction in the crystallinity and molecular dispersion of the amorphous drug in the compact. The reason for the appearance of the small peak at the same point might be due to the recrystallization of artemether. This could be because of complete solubilization of artemether in Twin 80, leading to supersaturation, and later a minor fraction of the molecularly dispersed drug might have been recrystallized to beta form again. Now, coming to the PXID study, the pure drug of artemether and the formulation 5 PXID diffraction patterns are shown here, and the characteristics peaks of beta artemether were seen at 2 theta angle of 9.88 degree, 17.64 degree, 18.04 degree, and 19.68 degree. This is the indication of the beta polymorphic form of artemether. The same peaks were retained in the formulation, but the peak intensity was reduced a lot. That indicates the crystallinity of the drug was decreased. The loss of this crystallinity in this liquid solid formulation may be attributed to the solubilization of the drug in the liquid vehicle and subsequent adsorption onto the carrier and coating material. Hence, here the proposed hypothesis would preserve the polymorphic form of artemether and also improve the dissolution characteristics. So formulation F5 was subjected for stability study at 40 degrees centigrade with 75% relative humidity for 3 months period. In intermittent time, it was taken out and tested for the following attributes like appearance, weight variation, hardness, friability, disintegration time, dissolution time, etc. And it was seen that as per IP, artemether lumefantrine tablet combination, there it is mentioned that the drug dissolution should not be less than 60%. So the limit value was 60%, but our formulation maintained the dissolution throughout the shelf life period at 90%, as it was observed in the test period. Therefore, the stability of the formulation also is established in this. The present research work, coming to the summary and conclusion, the present research work is focused on improving the solid state stability and dissolution of artemether by employing liquisolid compact technique using mesoporous silica as a novel carrier or and coating material. So the hypothesis suggested was that we should be able to screen the efficacy of the mesoporous silica and to find a suitable excipient ratio. We have achieved it, and we have seen that a mixture of Neusilin US32 and MCC at 9:1 ratio with Syloid XDP at an excipient ratio of 10 can be a good combination for liquisolid compact of artemether. Enhancement of the dissolution of the artemether also was seen because the dissolution also showed a marked increase, and it was further supported by the BET study as the surface area was improved, and therefore the drug release also was, the specific surface area improved, and therefore the drug release also was improved. Evaluating the polymorphic retention of the artemether through surface characteristic study, yes, it was achieved because solid state characterization by FTIR, DSC, and PXRD proved the polymorphic retention of the beta artemether, and the short-term stability study also showed the safeguarding of the formulation characteristics and firmness of both the varieties of mesoporous silica in the formulations. Hence, it can be concluded that the liquisolid compact of artemether using Twin 80 as a non-volatile solvent and mesoporous silicas as coating material and co-material can be an optimistic way to preserve the solid state behavior of the beta polymorphic form and enhancement of the dissolution of the drug. These are the few references, but they have helped us to find out and to carry out the work. Thank you.
Thank you so much, Madam Sayani Bhattacharyya. It was a lovely presentation.